Okay, welcome to our webinar today, introducing Project Antalya. We're going to show you how to scale ClickHouse queries infinitely with 10x cheaper storage. It is a pleasure to be here. This is a topic of wide interest to people, and you can look forward to an interesting presentation. Before we dive in and do some intros of our speakers, I'd like to give you a little bit of housekeeping information. This presentation is being recorded. We will send you a link to it after the presentation. We'll also send you a link to the slides so you don't have to take frantic notes. It's all being taken care of for you. You can post questions into the Q&A box. We will try and answer them as we go along. In the background, we have extra people on the call. You can, if you post them into the chat, we may or may not see them there, but we'll try. And finally, as far as questions, we anticipate that there'll be overflow on this, and we won't be able to answer every question, but we do have office hours coming up next week. We'll post the link for that toward the end of the webinar, so you can join that and come in and ask more questions live with us at that time. With that, I'd like to dive in and make some introductions. So my name is Robert Hodges. I'm CEO of Altinity. It is my pleasure to have with us Tim, who's co-CEO of PostHog. Tim, you want to just introduce yourself, and that'll also help us do a sound check.
Yeah. Hey, everyone. Yeah, like Robert said, I'm Tim. I founded PostHog with my co-founder about 5-6 years ago. I'll do an intro on what PostHog actually is, but we are big users of ClickHouse, so really excited about Antalya.
Great, and Tim and his team been a big collaborator on this effort. You'll hear more about that shortly. I'd also like to introduce Alexander Zaitsev, our CTO and the architect behind what you're seeing today. Alexander, if you want to just say hi.
Hey guys, happy to see everybody here.
Great. So that's it. Let me just introduce one more party here. That's Altinity. We help people build better on open source ClickHouse. We've been helping users build better ClickHouse applications since 2017. We operated Altinity.cloud, which was the first cloud for ClickHouse in the American public clouds, Amazon, GCP, now Azure, as well as Hetzner. We do Altinity stable builds. That's the enterprise open source build for ClickHouse. Many of you are already using another piece of software that we write. That's the Altinity Kubernetes operator for ClickHouse, possibly the most popular thing we've ever written. And we do ClickHouse backup, many other things. So it's our pleasure to introduce you to the next step, which is to be able to use Iceberg as shared storage. Let's dive into the talk and give you the whole story. So the way that this begins is in our experience, as well as your experience with using ClickHouse. 5 years ago, when we were beginning to manage ClickHouse in the cloud, most of the customers that we had were dealing with data set sizes that were in the range of a few tens of terabytes at most. So you could basically deal with those just using attached storage on a single host, of course, replicated for performance and availability. There's been a huge growth of data since that time. We're dealing with observability data sets that run up to 100 petabytes of data. Our customers are managing these, delivering sort of real-time analytics on them. And just to give you an idea of the scale of these data sets, there's one customer we're working with that is putting in 2 petabytes of data per day. This size is larger than than any of the other data sets that we were managing or helping people manage 5 years ago. So this is beginning to outstrip, and in fact already has outstripped, the capacity of open source ClickHouse, and it's leading to some very practical problems, mostly around storage and compute cost. There are, of course, other issues like just managing things when they get to this scale, keeping them up and running. But the thing that really strikes people and that we hear from customers regularly and we help them work around is, look, I'm looking at my cloud bill and I'm seeing a big chunk devoted to storage and devoted to compute for these real-time analytics systems. So there's 2 base causes here. One is that in open source ClickHouse today, the normal architecture for storage is to put it on block storage, for example, using Amazon EBS and then replicating it. So the effect here is that you get storage which ends up being pretty pricey. It's high performance, but if you compare that to storing the data on S3, it's about 10 times more expensive for typical systems. So this is problem number one, is how to get how to be able to get this off-block storage as much as possible and store data in a single copy on S3. Second problem, when you have large systems, you have a number of different types of applications or use cases that may be running against it. You may be ingesting data, you may be querying data, you may have different types of queries, batch versus sort of large scale reporting versus real-time dashboards. The problem with open source ClickHouse today is you have a single server that is meeting all of those requirements from the same process. You may have them multiplied, but what people end up doing is to ensure that they have adequate performance, they provision for the peak load, and it's hard to move things up and down in these and and adjust the scale to compute resources. What that leads to is wasted resources that just go on your bill. So this problem of dealing with large data sets in a scalable way and with cheap storage is not a new one. And in fact, what has happened over the course of the last decade is that data lakes have arisen to deal with this problem, driven primarily by usage in other types of workloads like batch queries or batch reporting, data science, and of course, AI training. So this started out with people just putting files on object storage, but over the last couple of years, we've seen an explosion in the number of people who are using Parquet. That's a columnar format, open, very similar to what Merge Tree does. And so we see that pervasively used inside enterprises today. And not only are people using Parquet, but they're increasingly using what are called open table formats, which organize those files into what look like SQL, into something like SQL tables. The most popular of these formats is Iceberg, followed by Delta Lake. Delta Lake is about these, when we talk to people, it's about 75% Iceberg, 25% Delta Lake. Delta Lake is very popular among people who are Databricks or Spark users. Why is this so successful? Well, obviously it's on object storage, so you've got you've got cheap storage, but thing number one is it's shareable. So you have one copy of the data and everybody can access it independently without blocking each other or increasing the amount that that we're spending on storage. Second is it's shareable. So which is really just sort of a variation on the single copy. Everybody can read it easily, and as I say, scale themselves independently. Third is open formats, and these are open specifications, Parquet and Iceberg. They're also backed by a wide range of open source libraries. In Python, for example, we have PyIceberg, which deals with the Iceberg part, PyArrow, which can read Parquet. These are widely used across and available across different languages. And then a final really important point is that these data lakes run just fine and in fact most easily in user accounts. That's part of providing accessibility, having them in your cloud account where everybody can see them and connect to them easily. So this is a good solution for batch. As we ask the question about how to apply it for real-time analytics, it's worth digging a little bit deeper into how Iceberg actually works. And the key here is that with open table formats like Iceberg, there's no longer a database that is gatekeeping the storage. In fact, you can think of this as being database storage that has been freed up so that everybody can access it regardless of the kind of client they have. Let's take a couple examples. So Python data science, an application there can pull in the Python and Iceberg libraries. And if we want to read, what we will do is connect to Iceberg. Nowadays, many people use REST catalogs, which make it easier, a single point of contact to get metadata, find out where the tables are, find out what files are in them. You pull that metadata down, and then the library will automatically help you find the Parquet files that you need to read in order to do a query on Iceberg storage. That's how reads work. So updates. Very similar process, except it's kind of a little bit reversed. What will happen is you write the Parquet files, and then once the Parquet files are out there, you will update the Iceberg metadata to tell Iceberg that, hey, there's a new version of the files in the table. This is the current state of it. When we try to do this, this works well for batch applications, but as we think about applying this to databases, there's a couple of problems that arise. One is that reading Parquet and on Iceberg can be very slow unless you do a lot of work to speed it up. So that's problem number one. Problem number two is it's hard to write to Iceberg. So there aren't very many libraries that support this. So it takes a lot of extra work to enable this write path and allow us to use Iceberg as proper database storage. We've been working on that, and that's in fact the core of what we're doing with Project Antalya. So there are multiple levels of innovation that are necessary to make this connection. The first is, okay, let's just make I/O really fast on Parquet data. And there's a variety of things that we need to do about this to make this work. We want to take advantage of features inside Parquet like Bloom filters. We want to implement clever hacks that make ClickHouse already run quickly on merge tree like Preware, where you use columns as indexes. We want to cache metadata so that we can decide whether or not we even need to look at a particular Parquet file. And we need to think hard about how to cache blocks that we're reading from S3. S3 is off board. The bandwidth is actually very, very good, but you still don't want to go to it unnecessarily for a variety of reasons. So that's thing number one, just make this fast. And we've done a lot of work, particularly focused on Parquet performance. The second thing is to apply cheap compute and specifically enable separation of storage and compute. For that, we're introducing stateless compute swarms. A lot of this presentation is about that. These are, and we'll tell you more about these shortly, but we're also introducing distributed caching as well as, in the very near future, tiered storage onto Iceberg. So you can store your cold data there automatically. So these are changes that happen inside ClickHouse itself and appear in new builds. The third thing that we're doing is ensuring that you can actually run this thing fast in real operational environments. There is more knitting and management than you think that's necessary to actually build systems that take advantage of this. So we're working on Kubernetes blueprints for things like auto scaling, cache deployment, Iceberg tooling, and monitoring, which allows you to understand performance. The result that you get from this is the full Project Antalya architecture. And the goal here is very simple. Let's make ClickHouse run fast and cheap on shared data, specifically shared data managed by Iceberg. So some of the things that you get in this architecture as we look at it are, first of all, when you connect to a native ClickHouse cluster, for example, from real-time analytics, you see all the data. Single SQL connection. It doesn't matter whether it's in Iceberg or or in native storage merge tree. You see it all. Second thing, if you have native ClickHouse tables, you want them to be able to extend seamlessly to a single copy on Iceberg Parquet. That's something that we're working to enable. Third thing is to be able to have flexible scaling of compute using, for example, cheap spot instances. That's what swarm clusters do. Final thing is deploy anywhere. So we're kind of focused on Kubernetes because it enables a lot of the auto scaling and deployment features that we want. It's portable, but you should be able to run this in any environment you want. It could be in a vendor account like ours. It could be in your account, managed by you or managed through a BYOC model, or it could be in an on-prem HPC environment. So we get this with the parts of Project Antalya. So the native ClickHouse clusters, that's ClickHouse running as it runs today, the swarm cluster, external cache, and then block storage. You have the Iceberg storage, which you can manage yourself, or you can use one of the emerging systems that are coming up like S3 table buckets, which are basically managed Iceberg. And so the final thing that falls out of this is, since we're storing things in Iceberg, that then opens up the door to sharing with things like event streams, Kafka Red Panda that writes straight to the data lake, as well as AI batch reporting and data science. So this is what we're aimed at. Let's go dig in on a couple of specific features. So stateless swarm clusters. So what these are, very simply, is they are just a pile of ClickHouse servers that have no schema, don't do replication, and don't have any storage beyond anything necessary to maintain caches. So this is your basic mechanism to implement compute, to implement compute storage separation. How do you use it? Well, there's a new property that you'll be able to use, or setting that you'll be able to use in open source Antalya builds. It's called object storage cluster. You just give the name of a swarm, and what that will do is, when this query is processed, as we go out to read the Parquet files, we're just going to delegate those reads out to the swarm, which will then go directly to Iceberg in parallel. So this is a huge speed up, and then of course the native ClickHouse cluster, the initiator will assemble the results and hand them back. But basically, all of the scanning activity is just going to be pushed out to extra compute and will not affect your existing ClickHouse systems. Now, the swarms are pretty flexible. I'm showing one, but one of the things that you can do is you can have as many of these as you like. And as you'll see, there are real use cases that Tim will illustrate where this is exactly what you want. So imagine that you have some queries that are coming into ClickHouse that are just for operational dashboards. You can put them in a swarm that is kind of always the same size and is configured at the right size for your constant load. You can have a second swarm that you bring up at time, at particular times, to support operations like batch reporting, which may require extra horsepower to scan the whole table as it exists out on Iceberg. So this is an important form of flexibility, and we'll show you examples of this in the demos as well as from Tim's talk. Caches. So caches make distance disappear. They are fundamental in distributed systems. They are particularly important when you're reading data from Iceberg. So let's talk about the kinds of caches that are available in Antalya. First of all, Iceberg metadata cache. When you're doing query planning, you don't want to be constantly going back to the Iceberg catalog, grabbing complex JSON files and parsing them. You really want them sitting in memory as much as possible. So that's handled by Iceberg metadata caching. Second thing, in the compute swarm, when you're actually running queries, you want to, if you read a block from S3, ideally you'd like to drop it into a file system cache. That's so those are configurable. Putting it into a cache that's written in local storage also has the effect of loading it into the buffer pool, so that when you come back to that block again, there's a good chance that the operating system will just find it in memory and hand it back to you. Another type of cache that's very important is Parquet metadata, so that we don't have to reread things like reopen Parquet files constantly to read min-max indexes, that we can tell, hey, is it safe to skip this file, or is it safe to skip particular row groups? That's a critical cache to making that run quickly. And then finally, external caching, particularly for HTTP requests. Calls like list objects on S3 data, where you enumerate files, are extremely expensive, and they only return, they basically are paged in the sense that they'll return chunks of files, say like 1,000 at a time. So being able to cache those has a huge effect on query performance, because you can avoid sending these constantly. So that's another big and important optimization. I'll just talk, these are all things that are available now that we're working on and you'll be able to play around with. Let me talk about two things that are coming in the future, and then we'd like to show you a demo of how this stuff actually works. Tiered storage. So tiered storage is a very, very important feature of ClickHouse today. It allows you to have hot data on a particular for example, on NVMe SSD storage, and then cold data to have that automatically move to cheaper storage for long-term preservation. So what we're implementing is tiered storage for Iceberg. And so the idea is that if you're doing a select from a user point of view, just like the way tiered storage works today, you'll select off a single table. And what we will do is split up the query so that we scan the hot part, we go straight to block storage. And for the cold part, we go out to the compute swarm and read it off Iceberg. And being able to, the fact that this is again where the swarm is important because it allows us to adjust the compute to manage this. Also, what you'll be able to do is use TTL moves, so time to live moves, which are simple settings that allow you to determine when the data actually moves off the hot storage and out into Iceberg. So this is a big feature. When this is enabled, it should drop costs by order of 80% in many cases. The final long-term goal is by opening up this use of data lakes as primary storage, we now are able to combine in many different ways and especially and build creative new types of applications. This is a complex picture that shows you some of the different types of things that we have in mind. I'm just going to touch on one to give you an idea of what this opens up, and that's materialized views. Materialized views are a great ClickHouse feature. One of the things that you will be able to do in future versions of Antalya is you'll be able to have materialized views that get fired automatically as hot data arrives directly in Iceberg. The materialized view gets built out, and then for your users, when they run a select, they can use the materialized view, for example, to look for outliers or other types of interesting events. And then when they need to zero in on the source data, they can run a query that goes out to the swarm and pulls the source records directly. So this kind of integration of native ClickHouse storage with Iceberg storage is something that in future will enable people to build very, very performant applications that also run on that handle large amounts of data but still keep the cost down. So this is an overview of what we're doing with Project Antalya. I hope this helps to helps you to understand what's going on. Swarm queries work today. We've been beavering away at these things now for months, and what I'd like to do is turn this over to Alexander Zaitsev, who's going to do a demo and show you some of the performance improvements. So Alexander, I'm going to stop my share and you can take over.
Yeah, thank you, Robert. By the way, we have a lot of interesting questions in the chat, and questions we will ask them at the end because they deserve some discussion. Let me share my screen. So what I'm going to show to you today is how swarm clusters work. We use Altinity Cloud as a test bed for that, but it could be run in any Kubernetes, so there is no magic here. We just use it as a UI and operational environment. And in this operational environment, I have 3 clusters that I will use today. One is my ClickHouse, and this is our entry point, and the one that we are going to extend, and another 2 are Swarm 1 and Swarm 2. They actually are launched on demand. You don't need to run them all the time. You can scale them totally independently. You see they have 5 shards, and my ClickHouse is just 1 shard, one replica. And if I need to, I can scale them totally independently to any amount of compute. And those are stateless. They don't have any data, any schema. This is just a compute. So let's try some queries. So first of all, we're running the special build of ClickHouse, which is called Altinity Antalya. We will talk at the end about how to find it, how to use it, how to contribute it. It is based on 25.2 version of upstream ClickHouse with a number of improvements that we contributed. And we will be rebasing it on the future ClickHouse versions, of course. We will start with a very basic query that will not use any swarm at all. So this is just a query to public blockchain dataset, querying all the data for the current year with some very simple grouping and aggregation. And if I run it, it typically takes 20 to 30 seconds to complete on this very small 2 vCPU machine. So the network is not very fast. It is just 2 vCPUs, so it cannot spawn a lot of threads in order to access S3. Maybe it will even time out because I have a 30 seconds timeout, but I hope not. It is done in 25 seconds. This is extremely slow for ClickHouse, of course. Yes, it had to read a pretty good chunk of data and a lot of rows, but we know that for ClickHouse, this is not something that that we want to use. So instead, what I will do right now, I will add a setting which will reference my swarm cluster. So as you could see, the swarm cluster, swarm 1, is totally separate compute. It's totally separate ClickHouse instance, but we have configuration that allows us to share those swarms. And this setting, object storage cluster, allows us to reference without changing the query itself. You don't need to change S3 to S3 cluster if you're familiar with ClickHouse. You just reference the cluster name, swarm name, and it could be a part of profile. I also disable file system cache for now. We will discuss why, just to avoid caching effects. When I run this query, and the query on a single node was taking 25 seconds, now it is down to 4 seconds. So this is already 6 times improvements. And if I repeat it a couple of times, maybe it will be even a bit more faster, but not too much. So it's already 2.5. I can also show that we, in addition to the reference in the swarm, we can also reference how many nodes we should use for the query processing. This is similar to ClickHouse max threads, as you may be familiar with. We can also specify the number of nodes. If you don't specify, it runs on all nodes available in the swarm, but you have fine tuning. And if I run it on a single node, then it will take something like 10 seconds. Let's check. Yeah, it is 7 seconds. And without that, I will be back to 2.5. Yeah. Now let's enable caching. So I just remove this because we have our cache enabled by default, and with file system cache, we minimize the amount of calls to S3. We don't need to run heavy network transfers anymore. And you can see the query time reduces dramatically. If I run it multiple times, maybe it will populate my cache better. So it is already 1.6 seconds, and it will be balancing about 1.6 2 seconds, depending on some different things. In fact, this is very slow. So we're using cache. We are not going to S3. Why it is so slow? And we were curious about that, and we have an answer, of course. Let me show you why. In order to get an answer to this, we should profile our query a little bit. So we are adding a comment, so we could see the query statistics for this particular query. I will check it right now. So this is the same query, and then we check our statistics. And as you can see, there was substantial amount of S3 list object calls, 13 in this case, that took almost 1 second. So the node initiator that was not supposed to do any job, it's still calling S3, and it's calling S3 very heavily. So the huge amount of our query processing time, maybe 50%, was spent on those list requests. So ClickHouse still needs to check what files are available, build this list, and redistribute it to the swarm. And this operation is very slow. Can we do it faster? of course, and this is where HTTP cache may help, and we are also working on implementing a different cache in ClickHouse specifically for this reason. In order to use HTTP cache, I will switch to a different swarm, swarm 2. It is pre-configured with the special distributed HTTP cache that caches S3 requests with different retention. For example, list requests are cached for 5 minutes. So if you don't update your S3 bucket very frequently, this is sufficient, and it may also cache the data. So let's check if it on a first call, it may be a bit slow because it needs to warm up the cache, but on a subsequent requests, I'm down to 1.3 seconds, 1.2. We want to get sub-second response time. We're very, very close. So what we can do, and here is one more feature, maybe the last one, almost the last one that I will show you today. We can actually delegate the full query to be run on a swarm and not on initiator. There will be a feature which is currently in development that will allow you to do it with a single setting. But before then, I will just use remote call to the swarm with remote function. And this will bypass all the work. Okay, it's still slow. Yeah, so now we're under 1 second. So that was our goal. So from 25 seconds at the very beginning, we're down to 700, 800 milliseconds. So this is how many? 40 times performance improvement from the original query. And we didn't change anything on the original ClickHouse. It's just the same small single node machine with a schema, with something else. We just added a swarm, which is totally separate cluster, and offload the heavy network and computer work to the swarm. You may ask, what about the Iceberg? Because we were talking about Iceberg a lot, and we will be talking about that. We actually have an Iceberg catalog as a part of Altinity Cloud. It will be available soon as a service as well. So this is one of the test versions, not final. And in this catalog, there is a table that we preloaded with the same data, AWS public blockchain that is represented as an Iceberg table. And we can run queries on this table as well. You may guess that it will use the same swarm approach. So for Iceberg, we use the same swarm approach. If you remove the setting, it will be very, very slow, and it might take more than 30 seconds. But with the swarm, it is pretty good, 2.2 seconds, something like that. Why it cannot be faster? Of course, it can be faster. We just at the beginning of optimizing Iceberg query pipeline, we already found multiple places where ClickHouse does some extra work that can be reduced. And at the end of the day, we expect that Iceberg performance will be superior to simple S3 bucket performance with the hive partitioning that we were using in original examples. So this is how you can do it right now. So you don't need anything but ClickHouse Antalya build, Kubernetes manifest, and that's it. And you can run those examples or build your own. So it is available already in open source. Any questions, Robert? Should I switch sharing to you?
I think we should switch sharing back. Let me go ahead and pick up the share. So thank you very much. And what I'm going to do now is, can you see my screen okay? Should be be visible. Okay, wonderful. What I'd like to do is turn it over to Tim, who's going to talk about how PostHog is designing for these new features and what they're going to do with them. So Tim, take it away.
Yeah, thanks everyone. So just a very brief sort of introduction to what PostHog is, just so everyone has a little bit of context. We basically provide all the tools in one platform that you need to build successful products. So that's product analytics, web analytics, session replay, a data warehouse, error tracking, feature flags, experimentation. We are also an open source project, which obviously also limits what we can and can't use for our software. So if you don't mind going to the next slide, Robert. This is kind of how PostHog uses ClickHouse at the moment. And the context here is that we store multiple petabytes of data, low double-digit petabytes of data. We ingest billions of events a day. This is kind of the basic setup of our cluster. I haven't put all of the nodes in. We have many more nodes in each of these replicas, but this is kind of give you a sense of it. So we have query coordinators, which are basically essentially stateless, also somewhat stateless, although we don't scale them up and down automatically at the moment, but they don't hold any of the data. They are just big nodes with a lot of memory, which then grab the data from the replicas and sort of collate them and give the final answer for these queries. We have a kind of an interesting set of queries. We allow people, obviously we do kind of standard analytics queries, right? So give you an overview of how many page views you've had over a certain amount of time. But these queries can get very complex. So we have, complex funnel queries. We even allow you to write kind of your own SQL. And so we have really, really large queries. Some of our real-time queries read, 20 terabytes of data. And so it's a relatively challenging sort of environment. We have divided it up into essentially 2 online replicas and then 1 offline replica. So generally in ClickHouse, you always want to have 3 replicas. The offline replica deals with anything that's kind of not immediately visible to the customer. So in our case, that's things like cache warming. It's recalculation of things like cohorts, and we actually offer our customers a version of materialized views. So the calculation of that lives in the offline replica. And then online replicas mostly serve queries in our interface to our customers. We also have some a portion of our customers' data lives in Parquet files on S3 at the moment. That's mostly data that customers send kind of separately. So that's things like their Stripe data, their Postgres data, that sort of thing. And we query those directly from the query coordinator as well. So this is our current setup. If we can go to the next slide. The issues that we have are kind of a couple here. Obviously, we have tight coupling of compute and storage, which means we can't easily scale up and down depending on workloads. Either we have to scale every node, and obviously in AWS, that means a 2x increase in cost. We either have to reshard, adding more nodes, or add another replica. The other issue that we have is all data is replicated 3 times on expensive NVMe and EBS disk. This, if we compare it to something like S3, like Robert said, I think we'd probably have a 10x reduction in cost. This is also why kind of adding another replica is even more expensive. We don't have reliable caching of block storage results. So like I said, we have a lot of data actually in Parquet on S3, and we don't have good caching of that. So we're basically always hitting real time there. If you could go to the next slide. So this is what we're sort of looking at with Antalya. We've spun up kind of a test cluster of Antalya, which looks really, really promising. We're about to deploy this kind of test cluster to use against some real world use cases. But the idea here is that we'll still continue having these coordinators, which are they will basically be kind of static, or they won't scale up and down quite as much in the same way that we have now. But then we'll have these swarm clusters that can dynamically scale up and down depending on our load. And because so much of it is driven by users, we have kind of that graph that Robert showed at the beginning, where it's really up and down during the day. That is very similar to our kind of graph of load. And so the ability to scale up and down elastically during the day is really interesting to us. But even more important, just as we're continuing to grow and scale, being able to scale up and down, mostly up really quickly is a huge help. And then yeah, we're looking at S3 tables. We're actually testing kind of 3 different ways of storing data in S3. We're using S3 tables. That's pretty nascent. So we're trying to figure out whether whether the performance is kind of appropriate. We're also testing AWS Glue, and then we're also just having kind of a native S3 with our own self-hosted catalog. So those are the 3 things that we're testing at the moment, and we're testing those against Antalya. Yeah.
Robert, you are muted if you're talking. Thank you, Tim.
Yep. Thank you, Tim. Yes, I was muted. I was thanking you profusely for showing what you can do today with swarm queries, or swarm clusters. Let's go and deal with some nuts and bolts issues and then get to questions, of which there are many. So what's the implementation plan right now? This sounds really great, but when do I actually get stuff so that it's useful? The swarm is now. So we are releasing this because it has reached a point where it needs to get into the hands of, it's already been in the hands of a number of our customers and users over the past couple months, but we want this to be generally used. You've heard a lot about that today. In May, we will introduce support for this directly in Altinity.cloud. The examples that Alexander showed you were set up manually, but we'll actually have UI for it. We will also be including some interesting Iceberg catalog tools, a way to populate catalogs, as well as good automation around the swarm clusters. So you'll see that coming on fairly quickly. Another thing that will be coming and is not showing here is this work to be done on the swarm fault tolerance, being able to deal with nodes, particularly going away. That's an interesting problem that we're working on right now. So there's work there. Later in the year, you'll get the tiered storage that we talked about. And then toward the end of the year, we plan to, well, we're going to be continuously optimizing the swarm autoscaling caching. Materialized views are very high on the list. That's a common request. So we'll try to get those as fast as we can. So that's the project plan. I think it's useful since we're talking about Antalya as if it's this new shiny thing, but it's a ClickHouse build with additional features in the same way that Altinity stable builds are ClickHouse builds or builds from upstream ClickHouse with some additional features. The difference is that Antalya has a lot more and it's a lot closer. We're not trying to keep these sort of stable at this time. We're trying to follow the head of ClickHouse development as closely as we can. So as you compare these, fast Parquet and S3 reads should be pretty comparable between builds, in part because we're taking the Parquet stuff we're doing and we're pushing it back up into upstream ClickHouse. This is stuff that should be shared with the entire community. Catalog support. Flow goes the other way. ClickHouse core team and community has done a lot of work on catalogs. We'll of course be helping with that, but those the capabilities you see there should be pretty much comparable. Where it begins to differ is, of course, the swarm clusters are specific to the Antalya builds. HTTP caching and additional settings as well as features to maintain these caches. These are in Antalya builds. Tiered storage, which is coming soon, will be Antalya builds. And then just the cloud native blueprints, all the information that's necessary to wire this together, build stuff that actually works. That's something that's included in Antalya and that you will not find as as part of official ClickHouse builds. So I hope that's helpful in keeping these things apart. Getting started, how do you begin using this? Well, today, as of yesterday, we have an examples project that is now opened up. You can just go ahead and clone it, and it shows how to bring it up in Docker as well as Kubernetes. Right here just shows you the commands. If you have Docker Compose installed, you can just cd into the Docker directory and type the script name, and you'll have a demo ready in about 20 seconds. It's great. I run it on my laptop all the time. We have things like build and contribution instructions. Let me tell you, these are still We're still building these out. We're very, very interested in contributions. I'll talk about that in a minute. And our goal is to make that as easy as possible. Speaking of contributions, the first thing you can do is just try this out, like what Tim's team has done. Talk to us, tell your friends, tell us what you're seeing. Tell us how this meets your use cases. If you want to talk to us, the simplest way to do this is to join our Slack workspace. Very easy link posted here. You can just go to our altinity.com page, punch the button, and you'll be in. That's the best place to have interactive conversations. We will do our best to keep up with them. And hopefully other people who are using Antalya can also chime in and help you understand how to get around problems or to suggest ways that we can do things better. As far as suggestions, definitely raise issues on GitHub. You can put them on the example project if it's documentation related or template related. Otherwise, they go against our ClickHouse branch, which we have in under the Altinity organization. And then finally, we love pull requests. That's one of the things that made the ClickHouse operator or the Altinity operator for ClickHouse. That's one of the things that made it great. If you are C++ enabled, we'd love to hear from you. This is a great way to make things run faster and build something truly great that's available to the entire community. So in summary, we'll get to questions here in a second. So exponential data growth, as Tim described, this 10x multiplication of storage costs when you're using replicated block storage is becoming an increasing problem as the data sets get large. And then, of course, the problem of being able to scale workloads up and down. This is leading to big costs for many, many users of ClickHouse. Iceberg solves the storage problem. And it is, of course, there's work to get there, but it is a solution that looks like the right pick at this point. And one of the reasons for that is the fact that it enables all workloads to share the same data. This results in synergies that are, some of which are already visible and some of which will only be apparent as time goes on. So Project Antalya is the work that we have been doing to make the query faster, to be able to scale things up and down, and to actually build systems that operate at scale using cloud-native methods. As we've said multiple times, code is 100% open source. It runs anywhere. I think for those of you who've worked with us before, those are two big things for us. And we have a roadmap, an aggressive roadmap to build this out as fast as possible, including tiered storage and then a deeper integration with other types of applications through shared Iceberg data. So please try it out and contribute. It's a community effort. We welcome contributions and would love to have your help. Credits. I want to first of all thank Tim for coming here today and also for sharing the work that we've done together with the PostHog team. You guys are great. I'd also like to embarrass Jump Trading. I think many of you know that they're very prominent in the ClickHouse community. A lot of the concepts behind this were developed in discussions for them. This is an issue we've been exploring now for years. And there've just been feedback, just day-to-day feedback with customers and community friends, really hundreds of conversations that have gone into the features and the design choices that you're hearing about today. And then finally, I want to thank the Altinity team for their work. There's 54 of us. We're spread worldwide. Everybody in Altinity has helped contribute to this. This is a picture of the engineering team hard at work, actually in Antalya, Turkey. So that's actually where the name of this project comes from. With that, let's turn it over for questions. I want to say that we have an office hours coming up. We'll post that in the chat. You can sign up for that. And we're going to have a follow-on webinar, which goes deep on swarm configuration, basically setting up for production usage. That's coming on May 21st. You can use that QR code to get in and sign up for it. Come and talk to us, showing just some links that you can use to get involved. With this, I'd like to turn it over and let's pick up some of the questions. Alexander, I'm going to turn it over to you because you've been watching these. If you have interesting questions that you want to highlight, let's start there.
Yeah, I will be happy to. So we have 19 questions, so we'll see how many we can answer. Marty, excellent questions about reliability and error handling. This is something that is not yet properly done. If there is a failure, then the query may fail. It is a bit better in terms of setup and monitoring. So if node fails, it will recover automatically because it's Kubernetes. We also use spot instances for this very aggressively because they are faster to start and they are faster to fail as well. So we will definitely address the failure issue in the next releases. Replicated replacing merge tree will work, but in a bit different way that it works now in ClickHouse. So it only can work in a tiered scenario when you have the hot tier, and this is where you're replacing merge tree and all modifications go to. As soon as you are confident that the data is not going to be modified, you can TTL it to the tier, the Iceberg tier, for longer retention and storage. It is possible to implement some updates on the Iceberg as well, but this is pretty hard. We can of course consider it for some scenarios.
Hey, Alexander, could I just jump in with a comment on that? Yeah, I think this is a wonderful. I was really glad to see this question come up because I think this is a wonderful illustration about why these data lake applications are going to be built with a combination of cheap storage for the long tail that's shared out in Iceberg, and then the hot storage, which is based on native ClickHouse structures. And a big reason why you want to do that is change. So it is much, much easier to change the native structures. And I think the replacing merge tree is the obvious example of that, where you need to be able to merge data to make changes appear. You can do that in the hot tip of the data, as Alexander says, and once it's settled, then it can be safely exhausted out to Iceberg. We're going to see a bunch of other use cases where this type of behavior is common, and that's why it's important to keep in this design. We keep everything that's in ClickHouse because, let's put it, y'all are going to need it. So I think really interesting opportunities here and some creative ways to mix these two storage types together.
Yeah, absolutely. So we're actually trying to use the most of ClickHouse and the most of Iceberg, and we're trying to use the solutions that work for merge tree and that prove that they work for merge tree and apply them for Iceberg and S3 data. So in particular, we implemented Bloom filter support for Parquet. Parquet as a format, it allows you to store this Bloom filter if application can write it. Now ClickHouse can read and utilize that. There are some other types of indexes already exist in Parquet, which are very similar to what you can find in merge tree and merge tree tables. And so we're trying to kind of move the experience that you used to have with merge tree to Parquet and apply all those techniques. So the question about,
quick request to the field. Please read the questions out fully so that.
Sure. I see.
Thanks.
Question from Timothy regarding comparing shared merge tree to Antalya. So that is actually one of the best questions here. The full motivation, or not full motivation, but 50% of motivation for Project Antalya was to overcome the limitation of community version of ClickHouse that doesn't have shared merge tree. So ClickHouse Inc. decided to keep shared merge tree as a unique feature for themselves, and community has been left without a good implementation for object storage. If you remember, we at Altinity started a community effort to build a replacement for merge tree, but it eventually was transferred to this Project Antalya. So instead of re-implementing this shared merge tree, we decided to move to this Iceberg, which in addition to giving users an ability to store data in object storage, it has a lot of other good properties like shared data, open format, and so on and so forth. So this is an alternative of open source to shared merge tree, and it has a lot of other properties. We cannot compare performance, of course, yet. It is from the different worlds, but soon we will have some comparisons as well. Question from Ali, is it possible to use Project Antalya for self-hosted ClickHouse? Of course, yes, and this is what you can find in Antalya examples that Robert has explained 10 minutes ago. It is all open source. You can install it. You can use everything on self-hosted ClickHouse or self-hosted ClickHouse cluster. Question from Gunharva, is Antalya available in GCP Marketplace? Altinity Cloud is available in GCP Marketplace, and you will be able to set up Antalya clusters with that in May. So right now it is possible, but in a bit manual way, we're adding automation to that. A question from Nathan, I'm not sure I understand that. Is using some sort of native style Kubernetes provider like AWS, Fargate, or Google Cloud Run as a source of Swarm compute on your roadmap? Actually, no. I think it is possible maybe in the future, but for now we consider that everything is running in one Kubernetes cluster because it allows us not to care too much about security, secure connections and stuff. If you want to use some external set of compute, of course it is possible, but you will have to configure connectivity properly. This is something that we can consider in the future releases. Question from Timothy, are you planning on merging this into the main ClickHouse repo or have a separate for going forward? In fact, and we tried to explain that we merge most of the stuff we try to merge in the ClickHouse repo, especially regarding to Parquet performance and stuff. Some features we don't merge to ClickHouse repo because they don't accept it. So we were facing that they don't accept our contributions. That may be a risk for the cloud version. This is why we have to maintain our own branch. It's not a fork, it is a branch of ClickHouse. We try to keep it in sync with upstream as much as possible and try to contribute our work to upstream, back to upstream as much as possible as well. Question from Arno about cache strategy. Right now it is random. You mean for HTTP cache, maybe, right? This is at the beginning. We started to experiment with distributed caches 2 weeks ago, and there is a lot of things that can be done here, including tuning caching strategy for different use cases. Question from Joseph, does it support dynamically changing the query execution as more swarm nodes come up during query execution? Partially. So if the same query is being executed and you add more compute during this query being executed, then it wouldn't affect this particular query because the query planning is performed at the beginning. But you can add more nodes to the swarm and new queries will use more compute or deferred compute. And we plan to do some automatic auto-scaling tools that would monitor the swarm workload and add or remove nodes when needed. Since we're using spot instances, this is going to be fast. What else? Question from Aditya, does Antalya also writes to Iceberg? Does it do something similar to shared merge tree in ClickHouse Cloud? Antalya currently cannot write to Iceberg. This is in development, and it's in fact in development from both ClickHouse core team and from us. Of course, we need to write into Iceberg if we want to support TTL and for other use cases. And yes, this may be considered as an alternative to shared. We already discussed it.
Alexander, I think it's worth pointing out that we're also kind of focused on writing parts initially.
Yep.
So that's because that is most consistent with the write patterns that work well on Iceberg. at this time, although Iceberg is, the spec is moving in the direction of being able to allow much better real-time write capabilities. And the second thing is not just moving parts, but being able to offboard the work to do that, because we don't want that crushing the compression that's necessary on to build Parquet parts can really crush your servers. It uses memory, it uses CPU. So moving that into the swarm is also another thing that you'll see.
Yeah, I think we're out of time. We will answer other questions offline. All great questions. Thank you very much for asking.
Yeah, and great. So we're going to call it, we're kind of running over time here. I want to emphasize again, we do have office hours. You can sign up for them under events at altinity.com. That'll be next week. Please do join our Slack channel. Please try the project out, give us feedback, log issues. As I say, tell your friends and make it better. And I'll give you an example, a couple examples of things that would be really interesting to try. One is using things like the new Cloudflare Iceberg buckets, as well as the Amazon Web Services S3 table buckets. These are really interesting innovations. And coming back to the questions that we've had about where else can the swarm run, there was a very interesting suggestion to try and run from Sentry to try and run these on Cloudflare durable objects. That would be super interesting to try. So as you have these ideas, try them yourself or come discuss with us. This is exactly the kind of innovation that will make this a really, really awesome piece of technology. It's something that if we do it together as a community, it's going to be great. I'd like to conclude by thanking Tim again. Thank you so much for joining us today, and thanks for the help on from PostHog. It has been a true pleasure to work with you. Also, we have some of the jump trading folks on. Thank you as well. It's users like you that make this job really fun. So we're going to call it good. We hope to see you out on the Slack channel, and we hope you enjoy Project Antalya. Good luck, and we'll talk soon.